Haloalkane and haloarenes, right?
Yes, sir.
And haloarenes, these are known as alkalalites, which you said very correctly that the halogen atom is connected to sp3 carbon, and these haloarenes are aryl halides or aromatic halides.
Aryl halides are bonded with sp2 carbon, right?
Yeah.
Or aromatic.
Exactly. sp2, and but you need to add something little bit more. Yeah. For example, so alkyl halides are, for example, I will write CH3F, okay, or CH3CH 2Br, okay. These are normal alkyl groups attached to attached to a halide. The halide can be fluoride, chloride, bromide, or iodide, right?
Yes, sir.
Okay. And this is primary, this is secondary, and this is tertiary. Is it clear?
Yes.
And aromatic halides are, first you need to know what are aromatic. So most common aromatic ring is the benzene ring, right?
Yes.
So earlier the concept was the compounds which had aroma were called aromatic compounds. But actually the compounds which have the cyclic resonance of electrons, in which the electrons are moving in a cyclic manner, 4n plus 2 electrons, they are called aromatic compound. So 4n plus 2 means how many electrons, you can put the different values of n ranging from 0, 1, 2, 3. You will get the number of electrons, right? For example, if you put n equal to 1, it indicates that 6 electrons. Okay, there are 6 pi electrons in the benzene ring, which are moving in a cyclic manner. Why they're moving in a cyclic manner? Why they're delocalized throughout the ring? Because they are adjacent, and such molecules are known as aromatic. So most common aromatic compound is the benzene, okay. And apart from that, we have aromatic compounds, okay. We have other aromatic compounds also, and that is naphthalene. Yeah, Nabil, can you hear my voice?
Yes, sir.
Yeah. So just I was going through the basic introduction of aromatic compounds, and if you have this is okay, bromobenzene, this is an aromatic halide. Naphthalene is also an aromatic compound, okay. So just we covered little bit Kulsum in the last class, okay, with Nabil. So what we can do is we can continue with the alkyl halide, okay, the topic which we were doing, and don't worry about the concepts. I will cover all the concepts, okay, and let me know if there is any problem.
Okay,
So
sir.
right, so Nabil, last time what we discussed? Yeah, tell me.
Sir, we saw electrophilic aromatic substitution.
Electrophilic aromatic substitution, right? Yeah. And what we prepared from that?
Sir, we prepared substituents of benzene.
Yeah. So how we prepare aryl halides? That's the question. And so first of all, suppose if I need to attach Br2, I need to take if I need to attach a bromine atom to the benzene ring, that is bromobenzene, I need to take Br2 first, but simply Br2 will not react. So what we did, yeah, Nabil, we had just started or we covered the mechanism? So first of all, suppose if you want to attach a group, the common way is to get it in the form of a plus, an electrophile. Why electrophile? Because benzene is having electron density. Okay, you can see there are 6 electrons. Okay, so an electrophile can come and join in to the get attracted towards the electron and it can start reacting. Okay, so suppose if you want to attach a bromine, you need to take Br plus. Okay, first of all, because bromine you can get it in the form of Br radical, you can get it in the form of Br minus, you can get it in the form of Br plus also. It depends upon how you react, how you treat bromine. Suppose if you treat bromine with sunlight, the Br2 break and you get Br radical, which has 1 electron. But for reacting with benzene, okay, this is electrophilic aromatic substitution, you need to generate a Br plus. And how you generate Br plus from Br2? Okay, that's very simple. You take a Lewis acid catalyst, right?
Yes, sir.
What are Lewis acids? Kulsum, tell.
Electron
Yeah.
donors.
Electron acceptors.
Electron acceptors.
Yeah. So Kulsum, what I have drawn, why I have drawn this box here? Any idea?
Orbital, sir. Empty
Yeah,
orbital.
empty orbital, right? Empty orbital. And this empty orbital, and you have taken a Br2. Okay. So what this empty orbital will do? Br has actually lone pair, right? 6 lone pair means 6 unshared pair of electrons. And this empty orbital, they get bonded to and through this Lewis acid catalyst accept the lone pair from Br. Okay, and what you get here is Br and Br2 you took, and Br and FeBr3, right? It is FeBr3 minus because it has accepted lone pair, and this will be plus, right? And now look at this bond. Look what it looked like before the Lewis acid was attached, and once the Lewis acid attached to one of the bromine, it became Br and Br plus. Okay, so now it is having one atom is having plus charge, so it can be broken more easily. Is it clear? So this Br will take away the electron density, it will break. Okay, and what you will get a Br plus. And the Br which is separated by taking away electron, that will go with FeBr3, and you will have FeBr3 was already there. One Br also came in and joined because it was Lewis acid catalyst. It was having a vacant orbital, FeBr4 minus. Is it clear?
Yes, sir.
Yes, sir.
Yeah. So remember what we did, what I told you. Suppose if you want to attach something to benzene ring, it will be convenient to attach that if you get that thing in the form of an electrophile. So we have Br plus. Now this Br plus will go and attack. Okay, look here, I have shown you the example of generation of Cl plus. Okay, clear. This Cl plus is an electrophile, so it will interact with benzene. It will, because Cl plus is an highly electron deficient species. It needs electron. So, and benzene is a rich source of electron, okay, because it has 3 pi electrons. Okay.
Sir, is it possible for you to send this PPT in WhatsApp, sir?
Yeah, PPT it may not be possible, right? You can take the screenshot. Let me know if you have any doubt. Okay.
Yes, sir.
Yeah, you can take the screenshot. You can stop me. You can ask me anything.
Yes, sir.
Okay. So what happens here is the Cl plus is there. The Cl plus will come and snatch away the electron density from the benzene. So look here. So one pi bond was there, that the 2 electrons they moved out like this, and the Cl, suppose this is the Cl, okay, and this came approached the benzene ring and taken away the electron density of one of the bond of the benzene ring, and here you have a plus charge. The plus charge on Cl became neutral because the Cl accepted the electron. Okay, for a moment the benzene ring got disturbed because it was initially neutral. It was aromatic. It had 3 pi bond. All the bonds were complete before the reaction, but at this moment when the Cl approaches and takes away its electron density from the benzene, okay, this benzene will have plus charge, right? And this plus charge can move within the ring because there are some more pi bond. There are 2 pi bond left in the benzene, so this plus charge can come at this plus charge can pull the electron density from the adjacent pi bond in the ring. It can come at various places. You can draw the structures. Okay, and this intermediate is known as, what's the name of this intermediate? This is known as sigma complex. Okay, sigma complex, and sigma complex forms when an electrophile which we generated by taking some Lewis acid and some substances goes and attack on the benzene ring. It takes away the electron density of one of the bond of the benzene ring. The benzene ring has positive charge, and that positive charge circulate within the benzene. Okay, but now it is not a complete benzene ring. Okay, it is known as a sigma complex. It is an intermediate. Okay, why it is an intermediate? Because it is having a plus charge. It doesn't have complete bonds. Okay, so we can't stop here. We can't stop at the intermediate stage. Okay, we need to get back our neutral product and also the product which is stable. So we can assure the stability if somehow we can convert this sigma complex back to benzene ring kind of a structure, because benzene ring is aromatic compound and it is very stable. If somehow we can get back our benzene ring, then it is very stable. Okay, so what how we will get back to our benzene ring? So what happens here is, remember this Cl minus which was taken away by the Lewis acid catalyst, or the Br minus which was taken away by the Lewis acid catalyst, okay, leaving behind Cl plus. That Cl minus will, because these reactions are reversible, this Cl minus can come and break away this H plus from the benzene ring. Okay, and if it happens, okay, what will be the final result? So the Cl minus will come. Cl minus is already having electrons, so it will take away the H plus. And what will happen? H plus means H without electrons, and H is bonded through this benzene by 2 electrons in the bond are there. I just now highlighted. You can see these 2 electrons. Okay, and H plus is taken away. What will happen? These 2 electrons will get back into the ring, and once these 2 electrons get back into the ring will become perfect again, right? It will be like this. the ring will become neutral again. The electrons have got back into the benzene ring, and the benzene ring is now complete. So what has happened overall is you generated Cl plus by taking Cl2 and the Lewis acid catalyst. Okay, in the absence of light, in dark, right? That also you should know. Okay, and the Cl plus will go and attack on the benzene by taking away its electron density, 1 pi electron density from it. Okay, the plus charge will form. Okay, but we need to get back our benzene ring. So Cl plus attacked benzene and taken away the electron density, and from the same place the H plus was abstracted by Cl minus. So those electron got re-entered into the benzene ring, and that's how the complete reaction will happen. This overall reaction is a substitution reaction. Okay, because H plus is substituted by halogen. Okay, Cl plus or Br plus. If you are doing the bromination, it is Br plus. If you are doing the iodination, it is the I plus. Okay, so this is substitution reaction, and because it is taking place on the benzene ring, which is an aromatic ring, it is an electrophilic aromatic substitution reaction. Is it clear? It is electrophilic. It is known as electrophilic aromatic substitution. Electrophilic, why electrophilic? Because electrophile was generated, Cl plus was generated, and this step is going to be the slow step because you are breaking the neutral benzene ring, pulling its electron density. Okay, and once this sigma complex form, the removal of H plus by Cl minus will be the fast step because you are getting back your benzene ring. Is it clear, the mechanism, right? So how you need to generate bromobenzene? You take Br2 and FeBr3, or you can take simply Br2 and Fe also, because Br2 and Fe will react among themselves and they will form FeBr3. Similarly, you can take Cl2 and FeCl3. That will give you the Cl minus will be taken away by the Lewis acid FeCl3, and you will get back to you will have Cl plus, which will go and attack on the benzene ring. The benzene ring will form a sigma complex, and finally the H plus will be removed from the site where the Cl plus attached itself. Okay, so this is how the electrophilic substitution happens. This reaction is a general reaction. It will be useful for all the subsequent chapters, not only for this chapter. For the preparation of nitrobenzene, you need to generate NO2 plus. Then only that NO2 plus will be the electrophile that will get attached to the benzene, and you will have nitrobenzene. Suppose if you want to generate methyl benzene or toluene. So if you want to generate a methyl benzene by attaching CH3, you need to get CH3 plus. Okay, this is a general mechanism which we will see again and again in subsequent chapters. Okay, in which you somehow manage to generate one electrophile, which is an electron deficient species. That electrophile goes and attack benzene ring by taking its pi electron, followed by removal of H plus from the place where the electrophile attaches itself to the benzene. And finally, overall, you have this kind of reaction, which is known as electrophilic aromatic substitution reaction. Is it clear? Any doubts? Kulsum and Naveen, tell me.
No, sir, it's clear.
Yeah, it is. So for benzene, it is very. I have not asked you where you should put the chlorine or where you should put the bromine, because on the benzene, if you look, it was a regular hexagon. Okay, where should I put chlorine? At this carbon, this carbon, this carbon, this carbon, this carbon. You can put the chlorine at any of the carbon atom. Is it clear? It is because it was symmetrical, but you can't do this on these structures. So suppose if I take toluene or methyl benzene, and if I do the bromination, in the presence of Lewis acid, what I'm going to get, where my Br will get attached on the benzene ring with respect to methyl. That's what I wanted to know. Yeah. Nabil, any idea? Kulsum?
And the para position
Why
or the
para?
ortho position.
Yeah, correct. Why ortho and para?
Sir, because of they have become electron rich groups.
Yeah, exactly. Methyl is electron donating group, and electron donating groups are ortho para directing groups. Right?
So,
And electron pulling groups or electron withdrawing groups, okay, they are actually meta directing groups. So bromine also has lone pair. So this is giving the its lone pair to the benzene ring. So in a way, it is also ortho para directing group. Okay. So where should I put this Cl with respect to bromine? Either at the ortho or at the para. And ortho and para are formed simultaneously. What is the reason? Yeah, tell me.
because both will be electron.
Yeah,
Sorry?
you need to look at the sides. Yeah, both positions will be electron rich. Yeah. And what about nitrobenzene?
Sir, it will be meta directing, sir.
Yeah, it will be meta directing. Correct. Because nitrobenzene is electron withdrawing group. Right? And electron withdrawing groups are meta directing. Do we always need Lewis acid to attach halogen? Or are there certain conditions where the reaction can happen even without taking Lewis acid?
Sir, when it can form positive cation.
Now, when it can form positive cation, or when the substrate, when the reactant which you have taken is actually itself so reactive that it doesn't require any Lewis acid.
Yes, sir.
Okay, so that happens in the case that happens. Okay, that happens for phenol, right?
Yes, sir.
So phenol actually is very much phenol and aniline. They have lone pair in them. So what happened? These lone pair actually get into the ring and they appear at this position. This lone pair, if you write in the resonance structure one by one, they will appear at the ortho and para position. Same is the case with aniline also. These two are very reactive form of rings. Okay, and these groups are very much electron donating. So here you don't have to take Br2 with Lewis acid. Simply Br2 in water is sufficient. Okay, and what will happen, one more thing which you will notice here is the reaction will occur simultaneously at three positions. Okay, because these rings are actually very highly electron rich. Okay, because of the electron donation by these groups. Same is the case with aniline also. For aniline, if you attach bromine, okay, you don't require any Lewis acid. And even without the Lewis acid, the reaction happens at all the three positions simultaneously because these rings are very much electron rich. Is it clear?
So this aniline and hydroxyl group, they'll donate or they'll withdraw, sir?
They donate. Okay, and how they donate, if you want to understand it, let me show you the structure. Methyl is donating group, and how methyl donates. Actually, this CH electron density that gets into the benzene ring. Okay, and suppose if you look at this bond, this is getting electron from the CH bond. Okay, so this is carbon. Carbon cannot make 5 bonds. Okay, if it is getting electron from the CH, it need to make space for those incoming electrons. So what it does, that it pushed away this pi bond. Uh, these pi electrons were set aside on the ortho position in order to make space for the, look here, this is the minus, these were the pi electron, and now this is as form. This minus can move further into the ring. Okay, it can, because there is a pi bond next to, on the next atom, so this minus can move and form a pi bond. But this carbon is making 4 bonds. Okay, though the 3 bonds are visible, there is one hydrogen also that you need to know, and this will get shifted here, right? So you can have negative charge at the para. Similarly, this negative charge, once it comes at the para position, it can push the pi bond ahead of it, and that's how the negative charge will come at the another ortho position, and it can get back. So it is the delocalization of electron density of the CH bond with the adjacent benzene ring, and it is known as hyperconjugation effect. Is it clear? Right? And this makes the benzene, methyl benzene, very reactive, and not all the positions become equally reactive. Actually, you need to draw the structure to make out that which positions are actually getting more enriched by the electron densities. Is it clear? So Br also has lone pair. So lone pair is sitting ideal. So what it does, it gets into the benzene ring. But actually, in the case of halogen, they are electronegative. So they are trying to pull also, and they are also simultaneously trying to give their lone pair. Okay, so it is in two-way. So halogens actually give their lone pair, but actually they pull their sigma electrons. Okay, because they are electronegative, they are non-metal, they have tendency to pull the electron of the bond through which they are connected to the benzene. So they make the ortho and para positions electron rich. I am putting partial negative charge. Is it clear?
Sir, so sir, so halogens are electron withdrawing or donating, sir?
Actually, they are. So there are two. These are two kind of traffic. So by resonance, they are electron donating. Okay, but if you look at the sigma bond, they are minus effect. So overall, they are electron withdrawing. Okay, but if you have a choice to do the reaction, you will still choose orthopara positions. Why? Because the lone pair actually appears in doing the resonance. The lone pair enriches the electron densities at ortho and para position. Though overall, the bromine is electron withdrawing because their inductive effect is higher than their resonance effect. The plus means they are donating, minus means they are withdrawing. So suppose if you look into detail, there's, for example, chlorine is there. So these electrons are pulled away by the chlorine, the sigma bonded electrons. Okay, this is known as minus I effect. And the lone pair actually are sent towards the benzene ring because they are sitting ideal. So it is better to have them get delocalized with the benzene ring. That's how they will acquire stability. So this is plus R effect. So always resonance effect is more powerful than the inductive effect. Okay, except in the case of halogens where the inductive effect is more powerful. So overall, if you say that are they so they, in the case of halogens, minus I effect is more than plus R. So overall, if someone asks that whether the chlorine is electron withdrawing or donating, My answer is the net effect is electron withdrawing because minus effect is larger than the resonance effect. Okay. But if someone says, okay, if it is electron withdrawing, then why it is not matter directing? I would suggest that draw the resonance structure, though it is electron withdrawing, but it is also simultaneously enriching the benzene ring at ortho and para positions by giving its lone pair, okay, which is appearing at ortho and para positions. Okay, and that is the reason which will tell us that why the bromobenzene is ortho-para directing. Is it clear? Any doubts? You may be having doubts. You can ask me. Okay. Anytime. Yeah, Kulsum and Nabil, tell me. Yeah.
Sir, what is the plus R effect?
Plus R effect is actually the delocalization of lone pair. Okay, suppose this is the benzene ring. The benzene ring has 5 electron density. Okay, it looks like a donut, right? Because these 6 electrons are moving like this. And suppose if you have Cl or OH, the lone pair, which is just an adjacent to these pi electrons. So what happens? It overlaps, and this electron density also overlaps with the electron density of the benzene ring. Is it clear now?
Yes, sir.
And it get into the benzene ring. It enriches the electron density of the benzene ring further to further level. But what are the positions which get enriched? They are ortho and para positions. Okay, so just remember that always the lone pair, the groups having lone pairs, what will happen? Actually, this is the overall electron picture, but one by one also we can show, we can bring in this lone pair, okay, towards the benzene. In order to make space for the incoming lone pair, I put this pi electron density aside on the ortho position. Okay, and this is how I'm trying to show how the lone pair of oxygen is getting involved in resonance with the benzene. Okay, and because the OH lone pair is donating its lone pair to benzene, so it is plus effect. It is electron donating group by the means of resonance. It is also called plus M effect. Okay. Yeah. So look here, what has the electron density is increased at the ortho position, then it will increase further at the para, then again ortho. So you don't have to draw all these structures. Just remember this thing. So lone pair don't have, the groups which have lone pair are electron donating groups. That's it. Is it clear? Kulsum, any doubt?
No, sir, it's clear.
Yeah. Nabil, any doubt? So what happened to nitrobenzene? Nitrobenzene and aniline are different. Okay. So aniline is like this. Okay. And nitrobenzene, if you try to look it by writing its whole bond in a complete form, it is like this. So aniline was having a lone pair. So this lone pair of electron was ideal. Okay, so it will overlap with the benzene and it will start moving towards the benzene ring, and that will enrich the electron density of the benzene ring at ortho position. So here the minus will come, it will come again at this position if you draw the resonance structure. Okay. But what about NO2? NO2 doesn't have any lone pair. It is having a plus charge. Okay. So you can't expect this nitrogen to give electron. It doesn't have any lone pair. Okay. In fact, it is an electron deficient species. It is having a plus charge. So it is desperate to take electron. So what it does, it pulled this pi electron density from the benzene towards itself. And this is called resonance. Okay. So this is electron pulling group. and it is how it is pulling. It is pulling by the means of resonance. So electron pulling group minus by the means of resonance minus R effect. Is it clear? Or it is also called minus M effect. Okay. So what and how it affected the electron densities on the benzene ring. So I have moved this pi electron like this. Okay. So from this carbon, the electron density has been snatched away, okay, by the NO2 group. So here you will have positive charge. This positive charge is electron deficient. It will pull the electron density from the pi bond, which is ahead of it. Okay, this pi bond, which is like this, it will become like this, and there is a positive charge at the para position, and this plus charge will again try to pull the electron. So there is again a positive charge at the ortho position, and finally it will again take back its electron density. Okay, and that's how you have nitrobenzene again. So actually structure is actually the mixture of all these structures. We are trying to show them one by one so that we can have the idea of what is going on, how the electrons are moving, where the places which are getting enriched or deficient by these electron densities. Okay, and so this is overall you need to write it like this. So this nitrobenzene, and there will be a partial positive charge. That's it. You don't have to write all these structures. Nobody will ask you. But you need to have them in your mind, and you need to recreate all these just in a short way, not in detail in which I have shown. Just I have shown because you need to have some idea. Okay. And once you have idea, you can use it again and again. No need to draw all these structures. Okay. This is a time consuming process, but you need to have it in your mind to get the correct answer. Okay. So Br2 and FeBr3, and we have just now seen that is the Lewis acid, and that will break away Br minus. So you will have FeBr 4 minus and Br plus. This Br plus will go towards the benzene ring, nitrobenzene. So tell me where this Br plus will attach. Will it try to attach itself at the positions on the nitrobenzene where already there is a positive charge? Will the Br minus attach, Br plus attach itself to the position where already there is a plus charge? Can that happen? No, because Br is an electrophile. This one, Br plus is an electrophile, electron loving species. So it can't, it will not be comfortable in attaching itself to the ortho and para positions, as we can see here, because of the presence of NO2 ring, there is a positive charge at ortho and para positions, and if the Br comes and try to join at the ortho position, it will be repelled away because same charges repel. So Br will not join itself to the ortho position. So which is the position which is at least not positively charged, and where Br plus can come and join in, that is a meta position because it is neutral. And that's how it is called as meta directing. Nitrobenzene is meta directing. Is it clear? Any doubt?
Yes, sir.
So just do this question. This is a difficult question. So there is one more thing which I would like to tell you. Actually, we discussed in our previous classes. Suppose just now we have seen this reaction. Okay, I will get back to the slide, and just a second we will get back to this. Suppose if we have taken Br2 and FeBr3, which generated Br plus, and the Br plus attached itself to the benzene ring at ortho and para position, those were the positions which were actually became enriched by the electron densities because of the CS3 group, right? But suppose if I take Br2 light or heat, what will happen? And I told you take dark, don't take light. Suppose if I take Br2 and HNO or Br2 heat, what will happen? Yeah, Kulsum, Nabil.
It will form Br minus.
No, actually, heat or light will break Br2 in equal way. That is called homolytic cleavage. Okay, but this is with Lewis acid. It was not a equal way of breaking. It was heterolysis, in which one was taken away as Br minus and you were left with Br plus. But if you have Br2 sunlight, if you have Br2 HNO, if you have Br2 heat, you will have Br radicals. Okay, the electron will, the Br2 will break and the electron will be give equal distribution of electron while breaking bond. Is it clear? Suppose
So
if you
it will
heat,
form only Br or
pardon,
so sir, if we put with H mu or with heat, it will form from Br to it will form only Br.
it will form Br radical. Yeah. But this is not the final product. This is just an intermediate. So if we have this Br radical, it will abstract the hydrogen. Okay. You will have CH2 radical. Okay. And this will again join with Br. So it is called photohalogenation reaction. Remember, photohalogenation reaction was used to generate alkyl halides. Okay, on sp3 carbon, if you want to attach a bromine, you need to take Br2 and light. But on the benzene, if you want to attach bromine, you need to take Br2 and Lewis acid. Remember, photohalogenation reaction of alkanes.
Yes, sir.
Also, though you were not there in the class, earlier class, but any idea about this photohalogenation? Also, any idea of photohalogenation? For example, if you take methane and if you mix it with chlorine and give sunlight, what happens? Chlorine, methane, and if you take Cl2, sunlight or heat, what will happen? This Cl will break and this H will break. Okay, remove them as HCl and prepare CH3. Okay, that is photohalogenation, the halogenation of sp3 carbon in the presence of light. Is it clear? Now we can move to this question. Yeah. So this is, it is a difficult question. You can't do it in first attempt. So this is which compound, first of all, tell me. C7H8. So benzene is C6H6. Okay, just have idea like this. So benzene is C6H6. So there must be some one carbon extra and some group one carbon also bring in some H atom along with it. Okay, so it is the toluene or methyl benzene. Toluene is the common name and this is the methyl benzene. So this C7H8 is nothing but CH3, okay, on benzene. Is it clear?
Yes, sir.
Right?
Yes,
And here you have taken not you have taken chlorine and sunlight or heat, but you have not taken Cl2 and FeCl3. Okay, if you would have taken Cl2 and FeCl3, that would have generated Cl plus and that would have attached itself to the benzene ring at ortho and para positions. But this is not the case. Okay, this is not the case. Okay, this is this is happening. This is happening at this CS3. Okay, is it clear? Right? Is it clear? So this is happening not on the benzene ring, it is happening on the methyl, which is connected sp3 carbon. This is the halogenation of the sp3 carbon. Is it clear? But so suppose if you take Cl2 and sunlight, you will have the reaction one time you remove HCl and you put Cl. But in this case, you have taken 3 Cl2. Okay. So it means it will happen 3 times and all the hydrogens will be replaced by Cl. So what is the structure of A? It will be CCl3. Is it clear?
Yes, sir.
Suppose if you take halogen in excess, methane if you take, and methane, suppose if someone gives you methane and Cl2, what you will prepare? Methane is CH4, okay, sp3 carbon, Cl2, okay, sunlight or heat, just one Cl2 is given, you will remove HCl and you put one Cl, that's it. That's the way you need to do the reaction. But if someone gives you excess, so what happens is the first mole of Cl2 reacts, it forms CH3Cl, but you still have some Cl2 left, right? So it will happen again and again. CCl4, yeah, correct. CCl4. So all the hydrogens of the sp3 carbon will be substituted by Cl, and that's what here it has happened. So all the hydrogens of the sp3 carbon were substituted by Cl. So this is A. Okay, and then you have Br2Fe. So where should I put the Br2Fe in this case? So we need to know
Orthopara positions.
orthopara. Is it like CH3? Though the formula look very similar to CH3. Also, would you like to add anything? So this group looks like CH3, but Nabil, these are not the hydrogen atom. These are chlorine atoms, which are highly electron withdrawing. Okay,
Yes,
is
sir.
it clear? So it is highly electron withdrawing group. So Kulsum, just try to recall what happens if you have electron withdrawing group, where the electrophilic aromatic substitution occurs. Okay, it occurs at highly electron withdrawing group. It occurs
Meta.
at meta position. Yeah, yeah. So it is meta. So meta bromo. Right? Clear? Kulsum, is it clear?
Yes, sir. It's clear.
Yeah. So now is ZnHCl. What do you expect from ZnHCl? Tell me. Zinc and HCl. What it do? Actually, zinc and HCl is a reducing agent. Okay. And it removes the halogen atom and it put the H plus in place of halogen. That is a strong reducing agent. So it is used for the reduction of alkalalites, two alkanes. Okay. So don't worry, actually, this is I've taken a tough question, a lot of concept we will discuss. Okay, and this is your first class. Okay, so you have not attended the last few classes, so don't worry about it, right? Just let me know whatever your doubts are. Okay.
Okay, sir.
Yeah, what happens if you take Z and HCl? These all the three Cl atom will get reduced. And someone may ask why there is a partiality. Why I have reduced only the CCl3 group? Why I have not reduced the bromine? Why? What is the reason? The reason is this bromine will not break easily. Being connected to the benzene ring, it is very difficult for the bromine to come out. Okay, so this reduction is for sp3 carbon, and you will get this product. Okay, so it is meta bromotoluene. So A will be your answer. Is that clear?
Yes, sir.
So it is a difficult question, so that's why I have kept it here. This is the next question. So Br2 and Fe means Br2 and FeBr3. Br2Fe and Br2FeBr3 is one and the same thing. If they just write Fe, the Br2 will react with Fe and it forms FeBr3. Okay, so you don't have to worry about it. Is it clear? So where should I put Br? Where should I put my Br atom? Which ring should I choose? The left one or the right one for the attachment of Br plus? First of all, I need to
Right one.
write one. Why right one? Yeah, your answer is correct. Yeah, right one. Why? You need to look at the groups or the atoms. Okay. Yeah, Nabil. Is it am I audible? Yeah, Nabil. I hope you can hear my voice. So this is the question. I this is in this I have asked where will you put Br. Okay, this is Br2 and FeBr3. Okay, Br2 Fe is same as that of Br2 and FeBr3. So where should I put my Br atom on which ring? So it is the right ring, which is more reactive. But why? What is the reason? Why it is more reactive? The reason is you need to look at the group. So this is doubly bonded O, and it is more electronegative group. Okay, and you can look here. This is just like the double bond O which was present on NO2. Okay, so because it is a double bond, it is and the other end of the double bond there is one more electronegative atom sitting. So what it does, it will pull the pi electron towards itself, and it will ultimately pull the electron density of the benzene ring. So benzene ring will acquire positive charge, and positive charge at its ortho and para positions. So this ring is electron deficient ring. And what about this ring? What about the ring which is on the right hand side? If you look closely, the right hand ring is you need to concentrate on the atom which is directly connected to the ring. And this is the lone pair. This is the normal nitrogen atom with a lone pair on it. This is similar to aniline, which we have seen. Okay, this is similar to aniline. So this lone pair will get into the benzene, and it will while doing so, it will push away the electron density, pi electron density aside at ortho position. The ortho position will again, the electron density will appear at para and ortho. So these positions will get enriched. Okay, and if you have Br2 Fe, it is same as that of Br2 and Fe Br3. Fe Br3 will break away the Br minus from Br2 and leaving behind a Br plus, right? And the Br plus will go and attack on the benzene ring. Okay, which benzene ring? The benzene ring which is more electron rich, which has negative charge, because the attacking species is Br plus. So where it can join itself comfortably, it will join itself comfortably at the positions which are more electron rich. So here you can see. So this Br plus will choose these positions of the right hand side ring because they are more electron rich. So let's see what's the right answer. So what's going to be the final
Can
answer?
you see how it forms positive? Can you see
Yeah.
again how it forms positive charge and negative charge?
Yeah. It is just like NO2. Okay, always remember, wherever you have a double bond and at the other end of the double bond there is one more electronegative atom sitting, this is the group which will pull electron towards itself, just like what had happened on NO2, nitro group. Why nitro group was creating a positive charge on the benzene ring? Remember? Look here, like this. Why we, and not only this, even the aldehyde group, carboxylic acid group, all those groups which have a double bond, we do not have lone pair. Instead, they have a double bond, and at the other end of the double bond or a triple bond, there is one more electronegative atom sitting. That electronegative atom will pull the double bond on itself, and this group as a whole will try to pull the electron density, pi electron density from the ring. So ring will have positive charge at ortho position, and it will move toward the para ortho. Okay. So that is why this ring is electron deficient. Okay, so final answer is Kulsum, what you were telling?
D.
Yeah, final answer is going to be option D. Yeah. Okay. Is it clear? Nabil, any doubt? Nabil, can you hear my voice?
Yes, sir.
Okay. So is it clear or not? Yeah. Nabil, you were preparing for JEE or NEET? Actually, I think you told me, but I forgot. You were preparing for JEE or NEET? Okay. So, Kulsum and Nabil, till now what we have seen that on the benzene ring, if you need to attach a halogen, you can attach it directly. Okay. And how you can attach it directly? By taking Cl2, but not light, by taking Cl2 and Lewis acid. Is it clear? You can attach halogen by taking chlorine and light. Okay. So that was a
If we,
direct, yeah.
if we
Yeah,
take bromine with light, it won't get attached.
pardon?
If we take bromine with light, it won't get attached.
No, it will get attached. It will get attached. Br, actually, okay, bromine with light. Okay. Actually, what happens is, suppose if you take light, what happens is, this is not an electrophilic aromatic substitution, that is addition reaction. With sunlight, actually, what happens is, all the bond breaks and the Cl atom get attached at all the 6 position, or Br atom will get attached at all the 6 position. So that is not electrophilic aromatic substitution reaction. So if you take Br2 and light, Br will get attached and all the 6 bond will break, 3 pi bond will break, and all the 6 position you have Br attached.
Sir, we can't do it by just adding one molecule of Cl2 or Br2.
Yeah, we can take, but you can't control it. You can't control it. Because what happens is, suppose if the reaction start, one mole doesn't mean one molecule. If you take even 1 mole, you will have 6.022 into 10 to the power 23 molecules. So what happened is, suppose we may think that we have taken 1 mole. Okay, so 1 Cl2 should get attached. But what happens is, the benzene ring will start the reaction. Okay, the next Cl2 molecule will react with that benzene only instead of choosing a fresh benzene molecule. It is because once the benzene reaction is started, aromaticity breaks, and now it can react more easily. Okay, that is the reason. So if you want to prepare, if you want to attach chlorine to the benzene or bromine to the benzene, always remember take Cl2 and take Lewis acid. Okay, clear? You can take Br2 and Lewis acid. That will be also. Yeah,
Yes, sir.
okay. You can take Br2 and FeBr3. You can take Cl2 and FeCl3. That is a different kind of reaction. This is not addition reaction, because the Cl plus will come and join in on the benzene ring, and the H plus will get removed by the Cl minus, which was generated with the help of Lewis acid. Okay, and these were the direct ways of attaching halogen, and this reaction, this mechanism is known as electrophilic aromatic substitution reactions. Is it clear? The one which we discussed. They proceed via sigma complex. Okay, and they will be useful in all the subsequent chapters. So those methods were the direct way of attaching, but there is an indirect way of attaching also. Okay, in which you don't attach your bromine or chlorine or fluorine directly. Instead, you choose some other route to bring in the fluorine, chlorine, bromine, and iodine. Okay, why do we need why do we need these methods? Okay, because sometimes it may happen that the question may be based on indirect methods. Okay, in which they are creating a chlorobenzene or bromobenzene, but not by doing its chlorination or bromination in the presence of Lewis acid directly, but they will give you indirectly. Okay, that is the indirect way of doing halogenation. So what's the indirect way of doing? Let's discuss it. So that indirect way of doing halogenation for preparation of chloro, bromo, fluoro, or iodobenzene is through diazonium salts. Okay, it is through diazonium salts. So what are diazonium salt? Okay, you can look here. I have given the structure of this is diazonium compound. So on benzene you have N2 plus group. It is called diazonium group.
Diazonium means only with chlorine, or it can be with any other ion as well, sir?
This ion can be anything. Cl minus, Br minus, F minus, or HSO4 minus also it cannot. This is the diazonium. So this is aryl diazonium or arene diazonium salt, and the salt can be chloride, bromide, iodide depending upon the anion. Is it clear?
Yes, sir.
So
So if they ask us to prepare like bromobenzene, which will be better one, sir? We can do by Lewis acid directly, or we have to go through diazonium group?
yeah, directly you can do it.
Yes, sir.
Directly you can do it. Diazonium need to be taken only under special conditions. What are those conditions? I will tell you. Okay. But sometimes the question, they don't ask you to choose your way. Sometimes they give you the question. Okay, so you need to remember that this is also one of the method to get Cl, Bri, or F attached to the benzene, but it is not the direct method. It is an indirect method, right?
Yes, sir.
So, okay, so why the Cl minus will get attached to the benzene? First, this is the structure of the diazonium compound. Kulsum, are you getting?
Yes, sir.
Yeah. So why this compound? Why with the help of this compound? What's so special about it? Why this compound will let us attach a chloride, bromide, or iodide to get attached to benzene? So there is this arene diazonium compound which you are seeing on the screen is not only for the preparation of chloride, bromide, chloride, iodide. It is used for the preparation of phenol. It is used for the preparation of benzonitrile, means you can attach CN. You can attach many other groups also. So this method which we are discussing as an alternate method to prepare chlorobenzene and bromobenzene is a very good method, because though the chlorobenzene and bromobenzene, it is an extra method, but there are certain other groups which can't be attached directly. So this is the only method by which you will attach those groups. Okay, so it is a very important method. Okay, so what's so special about diazonium? The special thing about the diazonium is, which group is this? Tell me. This is N2. Okay, N2 plus, right? Clear?
Yes, sir.
Yeah, and it will have a tendency to break away from the benzene ring. Okay, why it will break away? Because, and it will break away, how it will break away from the benzene ring? By taking these electron bonded to the benzene along with itself, so that it can come out as N2. And why it is so desperate to leave? Okay, it is because N2 is a very good leaving group. And who told us that N2 is a very good leaving group? Look at the composition of our atmosphere that has 70% nitrogen. Why it is having so much nitrogen? Because N2 is very stable. Okay, and if something is who is very stable, can come out very easily. So this is a very good leaving group, first of all. So we can take the advantage of this leaving group, and when it leaves, taking away the electron density and leaving behind a positive charge on the benzene, we can put the group of our requirement in its place. Okay, so all these methods in which you are preparing, in which you are putting group of your choice in place of N2, these such reactions are known as synthesis using diazonium salt. Okay, you can prepare aryl halides or aromatic halides, but not only aromatic halide, you can prepare a lot of other groups also via diazonium salt. Is it clear? So I have told so many things about the diazonium salt, but because the introduction was important. Now let's discuss how do we prepare the diazonium salt. Okay, I just told you this is the diazonium salt and how it can be used, what's so special about it, and why it can be used to prepare so many other functional groups on the benzene. Okay, that's what I told you. But how to prepare this? So these diazonium has nitrogen atom, you can see. So you should bring in some, so you take some benzene. This is ARH or some general aromatic compound ring. Okay, let's call it as benzene. Okay, so first you do the nitration, and again, if you want to attach NO2 group, you need to have NO2 plus. That's a general way of attaching an electrophile, which we discussed by attaching Cl plus and Br minus. They were generated with the help of Lewis acid. But how NO2 plus will get generated? You need to take some reagent which has NO2 in, and which is easily available in the lab. And all the labs have nitric acid. Okay, so have you seen nitric acid in your lab? Also, Nabil?
I have seen.
Yeah, it is what color it has having? It is having
Colorless, sir.
a pure is colorless, but it will be actually over a period of time it changes to yellow color. Okay.
Yes, yes.
Yeah, it will
I
be yellow.
remember.
Yeah, and you have to be very careful while handling it. And if it falls on your skin will also become yellow. Okay, and the yellow color it looks very ugly. Okay, if it falls on your skin, it will burn that skin, and that skin will become yellow, and it will continue to remain yellow for few days. Okay. Yeah, and it is because of the formation of xantho protein. Okay, that HNO3 react with the protein of your skin, and that
That
makes it.
happened to my skin once.
Yeah. Oh, so
It was there for 1 week, sir.
yeah. So that's a very ugly looking yellow, and it happened with me also. So I always used to scratch skin. Okay, but it never disappeared. It until unless the whole skin became old, and it was removed on its own. Okay. So this is a nitric acid. So it is there in all the lab. But this nitric acid, I need to generate an electrophile, electron loving species NO2 plus. Why not NO2 minus can fulfill the purpose? NO2 minus actually will, if we get NO2 minus, if we get it, okay, it will not attach itself to the benzene because it will be repelled away by the benzene, because benzene itself is having electrons, lot of electron on it, and NO2 minus is minus, it is also having electrons. So if NO2 minus approaches the benzene, it will be pushed away, it will be thrown away. So you need to, if you want something to happen, you need NO2 plus, which is an electrophile, electron loving species, because it's plus charge, so it can go and attack on the benzene by taking away its electron density. Okay, and what will happen? The H, which is present at the position where the NO2 plus has attached itself, that will be removed as H plus, and the electron will get back into the benzene ring, giving you nitrobenzene. Okay, this is EAS reaction, electrophilic aromatic substitution reaction. Okay, but how to get NO2 plus? So look at the structure of nitric acid. So nitric acid has NO2 and there is one extra OH. So if somehow I can manage to remove this OH group along with the electron pair, okay, I will get in my NO2 plus. Okay, so the same thing the same thing we did for chlorine. The chlorine, actually we generated chlorine plus by removing one of the chlorine atom along with its electron pair. Cl minus we removed, so we were left with Cl plus. That Cl plus started the reaction with benzene. So same thing, I need to remove this OH along with the electron pair. So what I did, I took acid which is much stronger, okay, and which is famous for the removal of water. H2SO4 is having a high tendency to absorb water. Okay, so it gives its H plus to OH, and that converts OH to OH2 plus. Okay, and this whole thing will be this whole thing will come again in our amines chapter also. So it will be very useful for you guys. Okay, and this water will be absorbed by the concentrated H2SO4, and you will be left with NO2 plus. The NO2 plus will go and attach itself on the benzene, forming a sigma complex, and H plus will come out, and you will have nitrobenzene. Okay, this is nitrobenzene. So at least we managed to prepare nitrobenzene. Okay, so nitrobenzene, how nitrobenzene is prepared? It is prepared by electrophilic aromatic substitution, which is also known by the name of nitration. And how do you do the nitration of benzene ring? You take nitric acid, okay, but nitric acid you need to remove the OH, so for that you took concentrated H2SO4. So you take mixture of two acid, nitric acid and H2SO4, that generate NO2 plus, and that is responsible for the nitration of the benzene ring. Okay, and this is the reduction. H is written, but you need to take some reducing agent, and I will write the reducing agent. It is metal and HCl. Just now we have seen in that question that FZ and HCl. So in this also it is the 10 and HCl, which is famously used as a reducing agent for nitrobenzene. 10 HCl or iron and HCl, very famous. Okay, and reduction means what? Reduction means removal of oxygen, addition of hydrogen, so your nitrobenzene will get changed to aniline. Is it clear? right? So this is the nitration method, and after nitration, we reduce the nitro group to aniline, but we need 2N and we need triple bond. So what we did, we took nitrous acid. This is the nitrous acid, HNO2, HO and NO. Okay, and this is along with HCl. Okay, salt and HCl. HCl again will remove the OH from the nitrous acid, HNO2, and you will be left with NO plus. Okay, so you already had aniline from the above reaction, and you took this NaNO2 plus HCl, which will give a nitrous acid. Okay, and nitrous acid, the water will be removed, and you will have NO plus left. NO plus is an electrophile, but now the electrophile will not get attached to the benzene ring because there is one other atom which can give its electron more readily to this NO plus, and that is NH2 of aniline. So that's how both get attached. Okay, you have NH2 plus and NO, and then what happens? Then finally in acidic medium, this water will get removed, and you have this pH N triple bond N plus. You have this diazonium salt. Is it clear? But you need to be very careful. You need to keep the temperature 0 to 5 degrees Celsius, right? You need to keep the temperature 0 to 5 degrees Celsius. Okay? Clear? Why we need to keep the temperature low while preparing diazonium salt? What's the reason? Kulsum and Nabil, tell me.
Sir, can you repeat? Sir, I was cut off from meeting.
Yeah, why it is necessary for us to keep the temperature low during the preparation of diazonium salt. The temperature for the preparation of diazonium salt is kept only between 0 to 5 degrees Celsius. Why? What's the reason? Kulsum, can you tell me? Can you explain me the reason?
Because they're unstable at high
Yeah.
temperatures.
Yeah, they are unstable. So we need to stop the reaction at diazonium so that we can put the group of our need, and we can get the diazonium N2 plus replaced by the nucleophile of our need, okay, which we want to attach. Suppose if you take high temperature, the diazonium will break away, okay, before you react with the group of your requirement. It will automatically on its own, it will break away and it will get spoiled. So you need to keep the temperature low while preparing diazonium salt. So let me summarize. I have said so many things, okay. Just quickly summarize it, okay. So first of all, you need to take benzene. You need to do its nitration by taking nitric acid and H2SO4. You will get nitrobenzene. You need to reduce the nitrobenzene by taking tin and HCl or FeHCl. Those are the two reagents which can reduce nitrobenzene with a very good percentage of yield. You will get aniline. This one. Now you react aniline with NaNO2 plus HCl. That will give, actually in the reaction it will form nitrous acid. Okay, HNO2. HNO2 actually breaks into NO plus. That NO plus get attached to NH2. Okay, PHNH2, NO plus, and the water get removed. And you finally ultimately have your diazonium salt. Is it clear? So this is the first part of preparation of diazonium. And during this, we also learned how to prepare nitrobenzene. Clear? Right? So now, how to use this diazonium? You can put the group of your requirement. This is a general way I have shown you nucleophile. This N2 will leave, and this place of N2 plus will be taken away by the nucleophile. The nucleophile will attach itself and N2 will come out. Okay. And that's how the reaction is going to happen. Right? Clear? So let's do this question quickly. Which of the following reacts with NaNO2 and dilute HCl at 0 to 5 degrees centigrade to form diazonium salt? So how diazonium salt is obtained? Which molecule is reacted with NaNO2 plus HCl that gives you diazonium salt? What's going to be the answer? Nabil and Kulsum, tell me quickly. Yeah, Nabil. Yeah. I think the voice is echoing. Kulsum, you can tell me. NaNO2 plus HCl is reacted with which compound in the last stage? NaNO2 plus HCl was reacted with which compound that gave diazonium salt? Okay. So look here once again. NaNO2 plus HCl was reacted with which compound? It was reacted with aniline. Okay. And aniline is the common name. Yeah.
Aromatic primary amine.
Yeah. Exactly. It is the B. Right. Very good. Okay. It is a B, aromatic primary amine. But amide and amide is a different functional group, Nabil. Okay. That is CO and ester. Okay. So you need to be very careful. And this is also a very good question. Just 1 month back, it appeared in the NEET examination, but very, very important question. Very good question. So primary aliphatic amine, that was aniline, was reacted with HNO2 or NaNO2 plus HCl. That is one and the same thing. That gave unstable diazonium salt. Diazonium salts are unstable, that we know, because the N2 wants to come out. It is a very good living group. Okay. The next statement reads, the primary aromatic amine react with NaNO2 plus HCl or HNO2 to form a diazonium salt, yeah, which are stable even at 300 Kelvin. So what's going to be the final answer? Yeah. Tell me. Nabil and Kulsum, just try it quickly. Very good question. It is B. Yes, correct. Very good. So this statement is correct. Primary amine react with NaO2 plus HCl, it gives unstable diazonium salt. But this statement appears to be correct. Primary aromatic amine react with NaO2 to form a diazonium salt, which are stable. So you need to read each and every part of the statement. Okay, that's the learning. So up till this point, it is good. There is no mistake. But is the whole statement correct? No. Okay, this is how many degrees? So just now we discussed that diazonium salts are stable only from 0 to 5 degrees, right? Clear? So you should read the statement, each and every statement, okay, completely. Then only you should come to a conclusion. The statement 2, initially it appeared correct, but the last part was incorrect. So the whole statement became incorrect. Okay, is it clear? This is correct. Primary aliphatic amine reacts with HNO2 to give unstable diazonium salt. Yeah, that is true. So you gave answer B. No, that B is not correct. Okay, I think I said it was correct. No, just check it. This is correct. And this temperature, this is incorrect. So third option is the right answer. Nabil and Kulsum, is it clear or not?
Yes, sir.
Okay, so you need to read each and every, even the temperature. Most of the time, even I also sometimes make the mistake. Okay, so you should also be very careful. Okay, always read even the temperature. Here everything was correct except the last point. The temperature 300 Kelvin was 27 degrees Celsius. And just now we discussed that while preparation of diazonium salt, you need to have temperature only between 0 to 5. So that makes the statement to second incorrect. So statement second is definitely incorrect, but this is correct. Primary amines, aliphatic amines also react. Okay, it happens with this also. Aliphatic amines also react, aromatic amines also react, but aliphatic amine actually they are more unstable. Okay, and they break very easily. Okay, so this is also true. You will see this reaction in amine chapter.